extremely hard place to measure vibration. You could have radiation, moisture, temperature differences. What you need is something with proven immunity to all these factors, and proof comes in the form of one of these, a calibration chart. Because otherwise you could get garbage in, and garbage in spells garbage out. And for those really tough environments, you need something like this, a tough accelerometer. You just want to check this out.
An engineering masterpiece, the Brawl & Keir Delta Shear Accelerometer. It's the best in the world. Use it properly and it'll repay your investment over and over again.
And that means we're already up to the third point. And I think we've got just about enough time left.
Okay, John. Commandment 3 is a bit of a tough one. But if you take it slowly and make it simple, you'll get through okay.
And when you're measuring vibration, you have a choice of measuring acceleration, velocity, displacement. Which one do you think is best?
Well, it must be acceleration, since you're using accelerators.
With an accelerometer, you get an acceleration signal. With a velocity pickup, you get a velocity signal. But from acceleration, you can integrate and get to velocity or displacement. On the other hand, from velocity, you can only get to displacement. And from displacement, you can't go anywhere.
I don't get that. I mean, where's this leading to?
Well, you see, the whole thing hinges on reliable, early fault detection.
Okay, check this out. This is the acceleration spectrum of a pulp and paper machine obtained using the signal from an accelerometer. We can integrate that acceleration spectrum to give a velocity spectrum, which looks like this. If we integrate again, we get this displacement spectrum. The point of all this being that the flattest spectrum, in this case the accelerometer spectrum, is the most reliable for early fault detection. That's because no component's too far from the mean level.
How many more of these have you got to go? See, I'm busy.
John, don't panic. He hasn't asked you to leave yet, has he? I think he's beginning to understand this stuff.
And tell me, Dick, why do your machines vibrate?
Go on, smartass, you tell me.
Well, you see, within machines, you have rotating parts, which cause forces to act. These forces are transmitted along a transmission path to a mounting spot where they're detected. But along this transmission path, you have resonances and anti-resonances. And the whole lot is governed by a mobility function, which has both a real and an imaginary part.
Imaginary part, crap!
John, how many times do I have to tell you to stop doing that? You've got to use the customer's language.
You can't judge much about the condition of your machine from a single measurement. What you have to do is establish a reference, and then look for deviations in the vibration level from this reference.
Does that mean I can't use a vibration standard?
Well, not exactly, but you have to use them with care. But if you follow me now, you'll see that I'm talking about a much more reliable, more effective way of condition monitoring.
We have to measure vibration indirectly. We measure the results of internal forces caused by faults inside the machine, but we have to measure them in the form of vibration on the machine's surface. A result of this compromise is that to judge machine condition on a single measurement is unreliable, since high vibration levels may be the result of high mobility in the transmission path. Or maybe there really is a fault, but how can you tell? The answer is to establish a reference level or spectrum and monitor changes. Because the mobility is a constant, any changes are typically related to faults.
So how do I know where to establish my reference and if my machine is in good condition?
Well, I mean, you have to use your experience, and you look like you have a lot of that.
You have to see your luck, mates.
Dick, calm down, Dick. Dick.
You've been warned.
I don't suppose you remember whether I was at 5 or 6, do you? Now, Dick, I'd like you to listen very closely to what I'm about to say. We've agreed, have we not, that you must establish a reference. But should that reference be an overall reference, or should it be a spectrum?
those fancy analyzers gets the guts out of me. I'd rather use a simple instrument.
Okay, that I can understand. And we recognise this. We produce a wide range of instrumentation of different degrees of sophistication. If you just look here.
Don't let machine condition monitoring scare you. Start with a simple system extending the human senses of hearing, seeing and feeling vibration. When you're ready, move up to the power and sophistication of spectrum analysis. Use a PC to organise all the measurements and all the machines. And when you get fed up with racing around the factory making measurements, connect your accelerometers to a permanent monitoring system, sit back, relax and just watch it all happen at over 500 points.
But the question is, where do you use the overall levels? If it's a simple machine, then it's a good starting point. But if you have a more complicated machine, then you must have a more complex system of monitoring, and that's spectrum comparison.
Don't knock simple measurements, they can be very useful in their place. Look at this measurement on a simple fan. Notice how one large component dominates the spectrum. So, when that increases, the overall level goes up. No chance of an unexpected breakdown there, is there? So here, the simple instrument's okay. But sometimes we have to be a bit cleverer and use spectrum analysis. Look at this gearbox spectrum. A critical component from the tooth meshing is nowhere near as big as the shaft component, so when those teeth begin to wear down, it doesn't show at all in the overall level until it's so big that the gearbox could already have failed. That could mean production losses, cash down the drain, or even the destruction of a valuable machine. So what do? We use the spectrum comparison technique. These two spectra are taken 3 months apart. Notice the growth of that component. The output shafts are definitely a bit dodgy.
Okay, so far what you've told me about vibration measurements and the spectrum comparison seems very similar to what I've seen from the other guys. What's so very special about your stuff?
Well, I was just coming to that. Without exception, they all use FFT, that's fast Fourier transform. We, on the other hand, use CPB.